just a couple more minutes. There's still people coming in, still people jumping online. Hope some of you got a chance to see the Northern Lights last night. They were visible all the way down in Austin. Unfortunately, way too much noise or light pollution in my neighborhood to see it, but I saw some great photos online. Just kind of unfortunate. I was just in Wisconsin 2 weeks ago for a conference, and I bet it would have been great to see the Northern Lights from up there.
Yeah, we definitely have too much light pollution here in LA too, Charlie. The only stars we see are the Hollywood kind.
Hey, stars are stars. All right. Currently sitting at about 28 people online. Let's see if that's going to change or not within the next minute or two. If not, we will get ourselves started. Just as I said, that jumped to 32. 33 now. All right, let's give it one more minute. Glad y'all could join us. This is great. Good turnout. All right. Well, hey everyone. Thanks so much for joining us on this beautiful Wednesday afternoon. My name is Charlie Day. I'm the DesignSafe training lead. With me today is Scott Brandenberg. We'll come to introduce him in just a little bit. If you haven't had a chance yet, please check out the story on the front page of DesignSafe. It's a very cool data set, um, all about how essentially it's about the first steps in home building and flood prevention on especially the first story homes. It's kind of a really cool data set to play around with. It's everything's linked on the main site on DesignSafe, so please do check that out. That's very, very cool. All right, so today's webinar is about introduction to scientific computing using DesignSafe JupyterHub. So as you all know, we build scientific gateways. And scientific gateways essentially gives you all the tools, the data, the expertise, and the knowledge base all in one location for you to hit. And that's what DesignSafe is all about. So we maintain this infrastructure for the Natural Hazards Engineering Research Institute, or NERI program. And we're going to be covering all the basics of scientific computing using DesignSafe's JupyterHub and are using our data depot. So if you may not know it, tax data depot, the DesignSafe data depot has 1 petabyte of data related to natural hazards. This is all essentially for you all to use and you all to be able to kind of run yourself through. So what we're going to be using today is Scott's going to be pulling some of that data that sits in our data depot and be able to run some numerical models on that, some analysis on it, and some machine learning on it, just to see what kind of tools you all have available to you and what those tools actually present. So for those of you who do not know, Scott Brandenberg is one of the PIs on the DesignSafe project. He's also a professor at the Department of Civil and Environmental Engineering at University of California in Los Angeles. And his expertise is all about geotechnical earthquake engineering. And I think that's probably one of the data sets he's going to be diving into today. So without any further ado, Scott, I'm going to hand off the screen duties to you. So thanks,
All
Scott.
right.
Appreciate you joining us today.
Thanks, Charlie. Let me get my screen share going. All right. Welcome, everybody. Thanks for being here. We've done this introduction to scientific computing webinar a few times in the past. Charlie's done a great job with these, and then Krishna, Kumar, and I have done a few follow-on ones. In the past, what we've done is solved a heat flow problem just to show some basics of Python computing. And for this one, we're doing something a little different. One of the real benefits of DesignSafe is that all of the data is there in the cloud, along with a JupyterHub that allows you to interact with the data. So the focus today is really more about how to find data sets in the DesignSafe data depot that you might want to interact with, and then how to find, you have to figure out the path and set the path to the files that you want to open. How do you open those files and work with the data directly without having to download it yourself? Of course, the Data Depot does allow you to download data too. You can go to a project and download it as a zip file. As Charlie mentioned, we have like a petabyte of data in there. That's a lot. If you have that much storage on your computer is way better than my computer. I'd like to just use Corral, which is the big file system on DesignSafe for that. One thing I want to mention, we have a DesignSafe CI GitHub repository that has some training materials in it. So I'm going to just paste this URL here in the chat. I'm going to be using this a lot to kind of go through the notebook and everything. And so if you go here into this content folder and click on this notebook right here, right? This is it'll do a preview mode for you, and you can see what we have here. And I'll just follow along largely from this resource. This is not going to be a hands-on webinar where I expect you to be able to type in what I'm typing in and follow exactly what I'm doing. I'm going to do things pretty quickly. This will be recorded. You could always watch back the YouTube video later, and you can use this resource. It has a Jupyter notebook right in the DesignSafe JupyterHub for you, and community data that you can open as well. So let me hide these meeting controls. All right, so what we'll be doing today is opening up data from a specific project. I'll show you information about the project directly through the Data Depot in a minute. It's a ground motion related project, but we're not going to focus a lot on earthquake ground motions. This is definitely not a technical presentation about ground motion. So if you're from a flood background or hurricanes, whatever it is, I think what I'm talking about today will be relevant, just as relevant as hazards in your own subfield of civil engineering hazards. So the data that's in here is part of this ground motion database. So I'll just mention this real quick. We have a whole website here, gmdatabase.org. If you're interested in ground motion data, you can go here and check it out. The data we'll be working with today is a subset of the data that's in this database. So we've expanded the database quite a bit since the data was published that we'll be working with today. So if you go to this website, you can check out a map, right? Like this map shows all of the ground motion recording stations. You can see they're distributed all over the world. New Zealand, not a whole lot in the southern hemisphere other than New Zealand, but obviously a lot in Japan and China, all through the Middle East and Europe. And then the United States obviously has a lot of ground motion data. You can turn on the events. Each one of those is an earthquake event. We have this beach ball feature that'll show focal mechanisms. It takes it just a second to load because it actually renders the SVG images on the fly based on the strike, dip, and rake for each event. So if we change the data, the image changes. And then you can also look at tables. So if we come here like to this time series metadata table, it has information, that you might be interested in, all of the information about how we processed a particular time series. If you come down here to the bottom, you can see we have now 191,000, more than 191,000 3-component records in here, including response spectra, intensity measures like PGA and PGV. We do have quite a bit of time series data, although not all of it is in here. And anyway, this is where all of the NGA West 3 project data are stored now. So I thought I would just mention that because it goes beyond the data set that we'll be using today. Oh, and there's also an API. I was talking to Charlie about that. Charlie will do a follow-up webinar about this, and he may want to use the API. I won't use it today because I'm really focused on using data that's published in the DesignSafe Data Depot. But if you are interested in developing a workflow around ground motion, the API will allow you to query just the pieces of data that you want into a Jupyter notebook, either at DesignSafe or on your own computer, and you can build your workflow that way. So that's one for another webinar. So let's go through first this to find the data set that we're going to work with. The best way to find the data is through the designsafe-ci.org webpage. So you can go here, use DesignSafe, click on the Data Depot. And then you'll see that you have, my data here. It takes it just a minute to load. You can see the my data folder for me is not particularly well organized. I tend to put my things in projects. So if you click there, this is a list of just all of the projects that I have. It's really a lot of them. Then if you go to published, here's the ones that have been published. So from the JupyterHub, you will have access to all of those folders, my data, your own projects. You can't access people's projects if they haven't published it, but you can access any project that you're a member of. And then you can access the published area, either just the published in DesignSafe or the published in NEES, which was, the Network for Earthquake Engineering Simulation that came before DesignSafe. So what I'm going to do is a keyword search for GMDB, stands for GM database. Click it, and you see these two projects pop up. And we're going to use this bottom project here, an archive of earthquake ground motion relational database for engineering applications. Basically, as we're building this ground motion database, we like to take snapshots and publish it at that time. And then it's like an official version that people can use. The database is kind of always changing. So if you were to use it directly in your workflows, you would face a reproducibility problem, right? Because maybe we'll change some data. And so it's good to take snapshots for reproducibility. This is one of those snapshots here. So let's see. First, if you wanted to, you could download the data set, right? We have a button up here. It'll download a zip file. You have to answer some questions and stuff like that. I'm not going to do that. I think that's kind of the old-fashioned way of doing our work. We would download data and then run it all locally from our own computer. DesignSafe offers more than just the data depot. It offers interaction tools as well. So what I'd like to do is just come down here and look at the structure of the data set. Okay, we have a README. If you want to, you can read that PDF. It basically tells you that what we've done here is to make copies of all of the tables from our database at a particular point in time, specifically right before we started adding data for the NGA West 3 project. And then we put it into these different folders. So the tables is like that'll contain a separate CSV file for each table. There's the schema that defines the organizational structure of the database. Then there's this flat files table or folder, and that's the one that we want to use. Basically, we take data from a lot of different tables and join them together based on key relationships, foreign key to primary key relationships in the database, and we make a flat file. So a flat file is just information from a lot of different tables. There's a lot of repetition in flat files. For example, we might record 2,000 different ground motions from one earthquake. Each row gets its own ground motion. So we're repeating event information 2,000 times for that event. Not a particularly efficient structure, but is very convenient for working with data. So that's what we're doing. And specifically, the one that we want to use is this one. This one that I've checked here, Rote D50 flat file version 1. So Rote D50 is a particular component of the two horizontal components of the ground motion. We record generally 3 components. We take those 2 horizontal components and rotate the coordinate system until we get the median shaking intensity for a particular intensity measure, and that's Rote D50. All right, so that's great. The question is, how do we interact with this data file? We want to open this in Jupyter and start interacting with it. So that's kind of what the webinar is all about today. So what I'll do is go here. This is the Jupyter notebook in the community data area. And so it's basically the same thing that you see in GitHub. If you click there, it has an open in DesignSafe link in the main repository. So you can open this and look at it yourself. One thing I'll mention about the community data area, it's read-only. So you will not be able to change this notebook. But what you can do is save it into your own My Data folder or into a project, and then you can edit it, right? If you wanted to use this as a base for building your own workflow, you could do it that way. So what I'll do is just go through this and show you, these are screenshots of things that I've already done, right? Search the data depot, find the project that you want to do, that you want to use, then look at the project structure. I'm a big fan of really thoroughly understanding data before I do any modeling of it. So definitely check out the README, read papers about it, stuff like that. And then here's the flat files. And what we'll do now is go to open this in the DesignSafe JupyterHub. Okay, so the complicated part about this, let's see, no Jupyter news, is to figure out where the file is located. So what I'll do here is go to the high level directory. Here we see those same folders, right? My data, my projects, NEES, NERI published. So what we want to do is go to this NERI published area. And the names are a little bit different, right? In the data depot, you see here published and then published NEES. They're a little different in DesignSafe, NEES, and then NERI published. Anyway, published is NERI published. So we'll click there. There are a large number of published projects. So when I click on that link, it takes it a minute to render. Here it is. Okay. One issue that we have is that in the DesignSafe JupyterHub, you don't see the project titles, you only see the project numbers. So this is not a great way to browse through projects and find the thing you're looking for. You really kind of have to have like a data depot tab open and then a NERI public, a JupyterHub tab open at the same time. But you can see here, right, this is project 5772. So we can scroll down to that project. Takes a minute to get down there because there's so much published data. I know I can do a control F for 5772, but it is nice to scroll through just to reinforce exactly how much data is here.
Yeah, for everybody who's curious, 1 petabyte of data. Typical database, typical data table is about 10 gig. If you were to load 10 gigs of data every day, it would take you about 280 years to get 1 petabyte of data loaded. So just think about how much 1 petabyte of data is. Sorry, Scott, just want to put that in there.
No problem. It took me a while to scroll anyway. So here I've opened up the project folder and you can see the flat files are here. So here's the file that we want to open, right? This flat file version 1.csv. So what we need to do is understand the path structure so we know how to get here, right? We can browse to it easily, but some of the parts of the path are hidden. So this notebook shows you exactly how to write out the path. By default, when you open up your Jupyter instance, you're going to be in this directory, home/Jupyter. And then everything else comes after that. So here's the NERI published folder and the project, and then the flat files. And then here's the GMDB wrote D50 flat file version 1.csv. So as long as we go to that folder and open that file, then we're good. So let's go ahead and do some of this. I'm just going to kind of walk through this Jupyter notebook and not type everything from scratch because I might make mistakes and then it's kind of boring to watch me type it in. So I'll just show you the code that I have typed and maybe explain a little bit about it. Like, why did I do it this way? So first, we're going to use Pandas to open the CSV file. Okay, Pandas is a Python package. I posted a link to it in the notebook. It's really good, in my opinion, for working with CSV files and data sets and things like that. I know people use it for analysis. I get frustrated with it, so I'm not a big fan of actually number crunching using Pandas, but for opening data, getting things in a data frame, and then extracting the data that we need to work with, I think it's great. You can do your workflow in Pandas if you want, but we're going to use Numpy to actually do some of the work here on the data set. And then we're going to use Matplotlib to make some plots, right? So here's the file. I just typed in the path relative to the home directory. Okay, another way of doing this would be to type a relative path, right? So I'm in the community data. We go back home. Here's the community data folder. And then let's see, we have to know where we are in training and then webinar, scientific computing 2025. So here's the notebook that I have open. What I could do is type a relative path, right? From this folder, go back 3 folders, and then go into this folder and use the ... notation and so forth. That's fine, that would work. The problem is that if you were to move this to a new directory or share it with another person who, it's just not going to work anymore. They're going to have to reset the path. So it's good to use the full path, just like I've done here. Then we read in the data into a data frame. And I'm using this low memory false keyword because if I don't do that, I get an error or not an error, a warning message. I don't like warning messages, right? So what low memory equals false means is that by default, pandas will try and load every column of data having a particular type. And so there are certain fields in this ground motion database, like station code, that has a mix of numbers and letters. Sometimes it's all numbers, sometimes it's a mix of letters and numbers, and sometimes it's all letters, like a string. That really should be a string field, but it's all numbers sometimes, and so Pandas gets confused and doesn't know how it should interpret it. And so low memory equals false just tells it, don't worry about data type for now. We'll worry about it when we read it into NumPy arrays. So I've read it. The file is, I think it's maybe 200 megabytes or something like that. So it's not like an instantaneous read. There's a lot of data in here. If you do this df.head command, it will show you the first 5 rows of data in the pandas data frame. So you can see there's like all these event ID, station ID, all this stuff. These are keys in our database. Public motion means that this motion is publicly accessible. Sometimes we have motions that we're still working on that are not ready for release. So that flag would be 0. And then our website knows not to make it available. Obviously, it is a published data set, so it's all available. Okay, then you see this ... little ellipsis here, and there's a lot of data in there, and it doesn't give you all the data. Then we get into these spectral accelerations. So if you want to, you can set the max columns option to be like 1,000, which I've done here. And now you can see all of the columns of data. This is still only the first 5 rows, but it's useful to know what all the columns are, right? There's a lot of them. So this flat file has a really large number of columns, and I think about 35,000 rows or something like that. So you can keep scrolling. You can see this is quite a big data file. I can see why you might not want to download this to your own computer if you could work on it in DesignSafe directly. All right, another thing Pandas is really good at is cleaning data. So a huge fraction of the time we spend doing research, building models, is kind of cleaning data. There's always problems with it. I'll give you a few examples of some of the problems you will encounter with this data set. So first of all, the PGA rote D50 values, that's the rote D50 component of peak ground acceleration, has to be bigger than 0, right? There's always some ground shaking that goes with any earthquake. But sometimes there's so much noise in a ground motion record that we can't really accurately measure peak acceleration. We might be able to get spectral acceleration at 2 seconds or something, but the frequencies that are influencing peak acceleration are too noise dominated, so we don't put a number. So that is either like a not a number, nan, or sometimes we put -999 as an explicit way of saying we don't know the PGA here. -999 is actually a number. So if you're not careful, you're going to get a whole bunch of -999 G accelerations in your PGA. So we don't want to do that. So what I've done here is said, let's filter our data frame so that we only get PGA rote D50 values that are greater than 0. Okay, and I'm using some notation here that will slice a data frame based on a condition. So this is the condition where the data frame dot PGA rote D50 greater than 0. And then I take the data frame of that condition. It gives the whole, it'll return the entire data frame, but remove rows where PGA rote D50 is less than or equal to 0. Similarly, distance has to be bigger than 0. There may be cases where we don't know the distance because we don't know the finite fault solution or something like that. And so we have a -999. I don't think that's the case, but I've filtered it anyway so that we get joiner bore distances greater than or equal to 0. Then magnitude, we have magnitudes that are smaller than 4. I've made a decision. Let's just plot magnitudes larger than 4 here. So we've added that filter. And then we're only looking at events that are in California. So we're filtering the data frame on 4 conditions. And now our data frame has been filtered to remove those things. You may have to do other filters depending on what you're doing with data and so forth. All right, then the next step that I'll do is take those data from Pandas. Oh, one more thing about Pandas I forgot to mention. I'm using a dot notation. You can actually do the same thing using bracket notation too. All of the names of my columns do not have spaces. So sometimes if your column name has a space in it, you can't use this dot notation. But you can do this, like df dot pga, underscore wrote d50, push control enter. It gives you a pandas series containing all of the wrote d50 data. You can also use this notation where you put it in quotes. And if I push enter, it gives me exactly the same thing, right? So if you have a space, you can't use dot. You can always use this string notation too. All right, so I'll delete those. Actually, I can't save anything to this notebook anyway, since it's in community data. Okay, I mentioned at the beginning, I'm not a fan of actually using pandas to do calculations. I do my calculations generally using a lot of NumPy or SciPy. So what we want to do is convert these pandas series into NumPy arrays. And that's really easy to do. You just put a dot values at the end, and you can either use the square bracket with text notation to identify a column, or you can use the dot notation that I'm using here. Once you put dot values, it will cast the pandas series into a NumPy array. So let me run that, run super quick. And then if we look at this PGA wrote D50 data, it's no longer a series, right? It's now an array. It's also not a Python list, right? It's a NumPy array, which means that we know the data type. Specifically, these are float valued accelerations. A Python list is different than a NumPy array. Python list is like basically a trash receptacle. You can put anything you want in there. It can be numbers, it can be strings, it can be an array, right? It's just like a garbage holder. So a NumPy array is much different. It has to be uniformly formatted and it's contiguous in memory and stuff like that. So it's more efficient to work with. I'll mention too that I use a lot of NumPy and SciPy in my work because there's always a decision to make. Like we can always write code using for loops and stuff like that. And it will do exactly the thing that we want it to do. But Python is very slow that way. Okay, Python's an interpreted language, not a compiled language. That makes it really convenient to write code in Python because you don't have to declare variables. You don't have to compile your code before running it. But what that means is that it's doing a lot of work at runtime to interpret your code and figure out what to do. So if you run a loop, like let's say I was to write a loop over all 30, I forget how many rows there are in this data set. If I were to write a loop over all of those, it would be really slow because at every loop, it's trying to decide, is this a float? Is this, what is this data? And so it's really easy to write Python code that is really inefficient. And I'm not talking about a 10% improvement. I've converted codes from Python loop structure into NumPy and achieved performance improvements of like a factor of 6,000, stuff like that. So if you have a heavy code, it really is worth the time to figure out how to use NumPy efficiently or SciPy or something that's already built, right? NumPy is not written in Python. It's written mostly in C. At least the heavy lifting part of NumPy is written in pre-compiled C extensions. So it's highly optimized and efficient. Pretty much every time, NumPy is going to be faster than if you write the same thing in Python using loops. So I'm going to use NumPy here. All right, so we've got our data in NumPy arrays. We're limiting it to really only a few features here, right? We have the peak acceleration. We have RJB, which is distance from a site to the surface projection of the fault rupture. Then we have the magnitude, and then VS30 is the average shear wave velocity in the upper 30 meters of the site. It's a measure of how stiff is the site. If it's rock, that's going to be a big number. If it's soft soil, it'll be a small number. 760 meters per second is kind of like the division between what we would consider rock and soil. anything down below 200 meters per second is very soft. So anyway, that's VS30. It has an impact on ground motion. And now what we'll do is go through and use Matplotlib, right? So Matplotlib looks like MATLAB, right? Sometimes I get confused, like, is this MATLAB? Matplotlib is not MATLAB. It's a Python package for plotting. And so what we'll do is make a figure here. And in ground motion modeling, we always make a plot of magnitude versus distance, just so we can see the distribution of the data that we're working with. This is important because seismic hazard tends to be controlled by big magnitude earthquakes at short distances a lot of the time, and we actually don't have much data coverage in that region. So we're always kind of extrapolating our models a little bit. So what I'll do here is create a figure and axis object using the subplots command. There are other ways of doing it. This is just the way that I tend to do it because I work directly with the axis object quite a bit. Then here, we're going to make a scatter plot, right? So a scatter plot just is individual data points represented by symbols. You can also make line plots, histograms, all kinds of things using Matplotlib. This is the scatter plot. And I'm just plotting RJB versus magnitude. The default symbol size is pretty big. So if we were to use the default Matplotlib symbols, they would be huge and they would all be overlapping with each other. So I've set it to 5. I think the default is more like 30, which would not work well for this particular figure. And then I'm going to make the edge color C0, which is the default first color for the Viridis color map that Matplotlib uses by default. You can change color maps too. Viridis is a good one for accessibility for people who have color blindness. And then I'm going to make the face color white so that the symbols just are a little blue outline. And I'll make the symbols appear on top of the grid lines. If I define the grid lines here after defining the scatter plot, by default, the grid lines appear on top of the data, which usually doesn't look very good. So I'm going to make the Z order 2 for the scatter plot and only 1 for the grid lines. And that way they'll show up on top of each other. If I run this one, right, we see this figure right here. So it actually looks a little bit different. I think I had adjusted the axes or something previously. But anyway, this is magnitude on the y-axis and distance here on the x-axis. A lot of data we have is down here in this range, right, between, oh, I think we're plotting everything down from 2 and high. Maybe, did I not run this one? I think that might be the issue. There we go. So now I've truncated the data so that it's only magnitude greater than 4. And that's the distribution of our data set in terms of magnitude and distance, right? Now what we'll do is move on to something that's more like what we might build a model on, right? This is more of a plot just showing data coverage. What we would want to do is model like acceleration versus distance. In general, the further away you are from a fault rupture, the lower the shaking is going to be. So we'll plot PGA rote G50 versus RJB. Ground motion models were originally called attenuation relationships. We've come to realize that there's a lot more factors that influence ground motion, so attenuation is just one part of it. And so ground motion model is a better indicator. But anyway, we'll run this one. And then I'm going to run this cell, make sure it works properly. Yeah, so we could make a plot just of PGA versus RJB. But of course, we have different magnitudes. So that wouldn't make a lot of sense because a large magnitude earthquake is at a particular distance would be expected to cause more shaking than a small magnitude earthquake at the same distance. So what I've done here is used some filtering. I put in magnitude bins here. So the first one is going to be magnitude 4 to 5, the second one 5 to 6, then 6 to 7, and 7 to 8. 4 bins. These are the bin edges. And I created a new figure. If I don't have this line, it will actually, this cell of the Jupyter Notebook would edit the previous figure that I've created. So I have to overwrite the figure and axis objects. You could also name these differently too if you want to. You can make new figure axis for each one. I'm overwriting the previous cell. And then I'm looping over the magnitude bins array, or this is actually a Python list. And so I just mentioned that I try and avoid Python loops. That's true, but this is only 5. Well, actually, I'm only doing 4 iterations of the loop, so that really doesn't matter, right? That's not going to make a big performance hit. You just want to avoid loops that go over all the data, especially nested loops, because it can be a lot of runtime overhead. So then I'm creating a filter here, right? I'm looping over from I equals 0 to 0, 1, 2, 3, right? Because each bin is in between 2 numbers. And then the filter is if the magnitude's greater than the bin on the left and less than or equal to the bin on the right. And then I use this NumPy array slicing, um, you know, notation to just filter out the RGB, PGA, ROT 50 that we want. And then I'm adding colors. Oh, I guess I'm not explicitly defining the color, but Matplotlib will go through its cycle of colors in the Viridis color map. So it's the blue and then the orange and then the green and then the red, right? And so you can see that one. We see clearly that there is an influence of magnitude. The blue ones are the low magnitude events. They're lower than the orange, and then the green ones are higher and the red ones are higher. Yeah. Okay, the other thing you might notice is that, boy, there's a lot of scatter, right? Earthquake ground motion data are highly uncertain. There's just a lot of variables that influence earthquake shaking, and it's really hard to account for all of them. So that is a common thread throughout earthquake ground motion modeling, is that there's quite a bit of uncertainty, and we quantify it and account for it. You'll also notice that it saturates, right? We don't tend to see this continuing to go up as distance becomes small. It kind of reaches a point where you're pretty close to the fault, and being closer doesn't change anything. And RJB actually can be 0. If you're on top of the surface projection of the fault, it's 0. And so that doesn't even show up in a log scale. So next, what we're going to do is a real simple multilinear regression, just to show you how you might work with data using NumPy. So we are going to build a ground motion model. I'll say from the outset that this is not going to be a good ground motion model. Nobody should ever use this model. It's really basic. Modern ground motion models account for a lot more things. This is just simple because we can do a multilinear regression. Most ground motion models have a functional form that's nonlinear. And this was one of the very early functional forms that people used in ground motion modeling. So it's just going to show you how to do some basic analysis here using NumPy arrays. So the functional form we'll have is the natural log of ground shaking intensity, right? Notice that I plotted PGA on a log scale here. It still is not quite linear, but anyway, we'll model it as multilinear. Is equal to a constant A plus a constant B times magnitude, plus another constant D times this natural log of distance plus a constant, right? Since distance has this kind of saturation feature and distance R can be 0 for RJB, we'll add a constant to it. And I'm just going to fix that constant to be 12 kilometers. A lot of the time we don't regress it. If we did leave C as a regression variable, our equation would not be linear anymore. So I'm fixing it to 12 just to make it a linear equation. And then we have our error term. So epsilon is the standard normal variate, and then sigma is the standard deviation. All right, so we have a linear equation. Ln of Yij is the natural log of PGA. Let's see, I is the event, and J is the site, right? So we have 2 indices. Magnitude is just an event property. Distance is a event property for that site. So it's Rij. We basically have a form like this. Ln of y is equal to the sum of beta times x, where beta is an array containing our regression constants or our model coefficients. And then the least squares solution for beta is just given by this equation right here. That's the least squares kind of pseudo inverse of this x array. So x is the array of our features. Okay, one thing that's maybe a little confusing is that we have a constant a, but it's not multiplying any feature. So how do we handle that? Well, we just need to make an array of ones, right? If we create a feature that's all ones everywhere, then that would become the first entry in our X array, and we can use the multilinear regression equation. So here we have this X is equal to an array of ones, the array of magnitude, and then this array of ln of RJB plus 12. And we can form that X and then solve for the betas. So really short set of coding here, right? This is one of the benefits of using NumPy is that it has solvers that use BLAS and LAPACK libraries, so very efficient. To form X, I'm just doing a VStack operation. That's a vertical stack where you can put together a bunch of different arrays. In this line, I'm creating an array of ones with the length equal to the length, equal to the length of RJB and of float type. And then we have the array of magnitudes and the array of the log of RJB plus 12. And then those three things are grouped together inside of a tuple. So there's parentheses around those. It's not a, this is a single entity that gets passed to VStack, which is a tuple. It's easy to forget that, and then you'll get an error. And then our Y parameter is just the log of rho T50. Then we have NumPy linealg, that's a linear algebra pack, and then solve, right? And we put in X times X transpose. I forgot to mention this VStack actually gives you the wrong shape compared to what the solution is up here. It gives you the transpose of X. So I've just switched where the transposes appear in this equation. So X at the ampersand is the array multiplication operator, and then we have an X transpose, and then we have X at Y here, and it will solve it and give us the beta. And so there's all of our model coefficients. And then we can see how good this model is, right? We can go to a residuals analysis, and I'm going to define residuals as the natural log of the measured PGA minus the prediction of the natural log of PGA from our model. And the predicted natural log is just beta X, right? A matrix multiplication. So here's the calculation of residuals on this line, Y minus beta X. And then we can print out the standard deviation of the natural logs of the residuals, 1.12. That's actually a pretty big sigma, right? We're talking about natural log sigma here. Modern ground motion models have sigmas that are more like 0.6 to 0.7, depending on the intensity measure for the total sigma. This one is really big. So that's an indication that our model is not particularly good. There are a lot of things that influence ground motion that we're not considering here, like VS30, like style of faulting. There's regional variations. There's so many things that we're not considering with this basic model. So then in ground motion, we always do residuals analyses, right? This is how we figure out if we can improve our models. We just plot residuals versus various unmodeled features to see if that feature might have some predictive power. So here's VS30. We're going to plot that versus the residuals. And then I'll create the plot and show it here. So all these blue points are our residuals, and this is the VS30. You tend to see vertical stripes here. And the reason is that the same site might record ground motions from multiple earthquakes. And so the VS30 for that site is repeated. So this vertical stripe is probably one location where VS30 is like just over 2,000 meters per second. There's some down here around 100, even one less than 100. It's actually, there's so much data that it's really hard to see the trend in it, right? There actually is a negative slope here. It's, at low VS30, we're having positive residuals. That means that the measured ground motion was bigger than the predicted ground motion. So we're under predicting it. And then at high VS30, we have negative residuals, meaning that we're over predicting. So indeed, VS30 does have some predictive power for us, and we could potentially improve the model by adding a VS30 term to it. What we see here is that I've added these bin means, right? The orange points are kind of local averages of all of the residuals within a particular bin. And it's useful to kind of understand how to do that just by using NumPy slicing. So here I'm making 50 bins. Then this is a really cool command that NumPy has called argsort. So this is exactly the kind of command that might require you to write like nested loops of your own that would be super inefficient if you wrote it in native Python. But NumPy has a solution, argsort. So me and my research team spend quite a bit of time trying to figure out if there's an existing precompiled binary that will do the thing that we need it to do so that we don't have to write our own Python code to do it. Argsort will basically figure out the ordering that you have to make to sort the array in an ascending way and give you those indices. So that's the list of those indices. We can plot what those look like here. So it's an array that just shows you the index of the location. And if you were to basically order the array by these indices, it would be sorted in order of increasing VS30 in this case, right? Since we did argsort on VS30. So then I'm also using an array split function. So NumPy has an array split function built in, so you don't have to do any loops. And it will take this sorted array of VS30 and divide it into in bins number of roughly equal sized bins. Now, unless the number of bins if the number of data points is an integer multiple of the number of bins, you would get equal sized bins for all of them. That's not generally the case. So this returns actually a Python list, not a NumPy array, because NumPy arrays have to have the same number of elements in each row or column. And then we're getting the residual bins using a similar thing. And then I'm defining empty arrays here for the bin means for the VS30 and the residual. And then since the array split command returns a list, I'm actually using a loop to compute the bin means. But again, this loop is only going over 50 elements, so it's not causing a big computational inefficiency for us. And that's how I plotted these orange points here. I like to do my bin means based on data density. So roughly each bin mean has the same number of data points corresponding to it. Okay, another way of doing it would be to say one bin is between 100 and 200, then between 200 and 300, and you can plot bin means that way. But each one will have a different number of data points and a different standard error and so forth. All right, so we're nearing the end. I want to be sure to leave some time for questions. So I'll just provide some conclusions here. We see that the residuals are biased. We could do better, right? Charlie will present a follow-up webinar that uses some machine learning techniques to interrogate these data, go a little deeper than the simple multilinear regression. That'll come soon after Thanksgiving, so please keep your eyes out for that one. And hopefully you've learned now how to access data directly in the data depot from JupyterHub, so you can make use of this petabyte or so of natural hazards data that we have. So I think that with that, I will stop sharing, and I'm happy to answer any questions. And I guess if you have questions, you can post them to the Q&A or the chat. Or Natalie, I think we have the ability to unmute people too if they want to ask it directly. Is that right?
Yeah.
Yeah, if you'd prefer to ask it instead of typing it, you can maybe raise your hand and we can call on you. Okay, so there is a question in the Q&A. I missed the earlier part of the webinar. Will a recording be available to attendees? The answer is yes. So all of our webinars are recorded, and you'll be able to find it on the DesignSafe YouTube channel afterward. And we'll put a link to the resources too, the GitHub resource and so forth, showing the notebook. Oh, and then one in the chat too. Why didn't you use scikit-learn for the regression? I could have. right? There's a lot of different ways to do this. Scikit-learn has a lot of really cool tools, and it can give you standard errors. I think it can do linear mixed effects regression, so that's very common in ground motion modeling. There's a lot of ways that could be better than what I did, right? What I did is very basic.
Yeah, we're going to play with some of the scikit-learn models at the part 2 of this webinar. So stay tuned.
Yeah, yeah. Scikit-learn can also do some basic machine learning stuff, right? Random forest and that, I think.
Yeah, yeah,
You could also do clustering. So if you want to do
yeah.
your
Sure can.
means by clustering, you could do that too, right?
Yeah, scikit-learn really is pretty awesome.
All right, great. I'm not seeing any other questions. Do you have a wrap-up slide, Charlie, showing like
I do, answering
or
that question from before. So let me just do the wrap-up slide and
oh
see if
wait, there's another one here.
there we go.
Do you have any references for improving Python coding skills? There's so much out there. I guess what I would mention is that Charlie has some really good webinars that go in more detail into coding for that heat flow problem. So you can find those in our YouTube channel. And then Krishna and I have some stuff on, I think, like accelerating Python, right? So it is really easy to write very inefficient Python code.
Yeah,
And so we have that for accelerating it using Numba, JAX, NumPy. There's all kinds of different ways of making things faster. So check those out too. Actually, the GitHub link that I posted in the chat has multiple training webinar materials there. So check out the DesignSafe CI training GitHub, and it'll have some resources for you.
yeah. The number one way I've learned from Python is just doing stuff, Googling stuff, researching stuff, because there's always better ways. Uh, I'm always under the impression that at least 5 or 10 years ago, nobody really was a great Python coder. We're all just good Python coders. Now, after looking at other people's Python code, yeah, there are definitely great Python coders. Well, the thing is, Python is just such I want to say the word elaborate language, and there's so much in it. I'm always discovering things like, oh, wow, I didn't know I could do that in Python. Oh, wow, I didn't know I could do that in Python because it's this ever evolving language, which is why it's used in so many cases, right? Here at TAC, our DevOps use it, our data guys use it, our developers for these science gateways use it, our HPC coders use it. Yeah, so it's got so many different applications. There's always more things to learn, and there's always new things being added to the language as well for these modules. So yeah, just start playing with it. Watch other people. Watch some YouTube videos. Watch some live coding demos, and see what type of habits people have, and try and incorporate the best habits into your own.
Yeah, and I'll just add, it's an interpreted language, which makes it really convenient because you
Yeah,
don't have to declare variables and allocate memory and do all that stuff that you have to do in a compiled language. But it also makes it prone to inefficiencies. So
yeah,
you have to weigh the
right.
efficiencies of quickly writing code, which Python's really good for, with the potential inefficiencies of doing heavy calculations. And so in that case, good Python coding involves not using Python, right? Using precompiled binaries that have a Python wrapper that you can make use of.
Exactly. One great example I always give people, let's say if you're going to write a sort program in Fortran, and you could write it from scratch and you do all the stuff in Fortran, it's really quick. Do that exact same sort routine in C++, and you're going to notice maybe a little faster, but about the same. Then you write that same sort routine in Python, it's going to be about 6 times slower. However,
Yeah.
Python has a built-in sort routine that if you just used it, it is actually faster than C++ and faster than Fortran. Thing is, it's got all these little nooks and crannies you kind of have to dig in to find these things. So yeah, and that's what kind of gives Python its charm. So anyway, somebody mentioned earlier about these videos being online. So if we do have a training archive, so if you go to DesignSafe and go to the Learning Center, all of our videos are archived there. They're linked also to DesignSafe's YouTube channel, so you can always go there and go back to the other ones as well. There are some additional little tidbits on use cases and these little tidbit videos on using particular parts of DesignSafe, which are on those YouTube videos as well, little 5-10 minute demos. So a lot of useful stuff there. I would highly recommend going and checking those things out, especially if you're new to DesignSafe. And of course, finally, thanks so much, Scott. Really appreciate your time. Really appreciate your efforts, over these last few years in getting the DesignSafe training up and going and becoming kind of a common place for people to come to learn more about scientific computing and DesignSafe and natural hazards. Thanks again for your efforts, Scott. Really appreciate it. And of course, thanks to our PI, Ellen Rathje, our Deputy Director of DesignSafe, Tim Cockrell, the director here at TAC, Dan Stanzione, and then everybody else who makes everything going. Thanks a lot. Big thanks to Natalie for getting these things organized for us. With that,
So Charlie, before
yeah.
questions came in, maybe we could answer
Oh,
those.
you got some more questions, of course.
Also, I don't know, are you showing a PowerPoint?
This,
We're,
yeah, I mean, this is not
we're
coming up.
seeing like an article summary, flood
Oh,
prevention. I think you
oh
maybe
yeah,
should.
yeah. Sorry, it's wrong screen. That's weird. I wonder why that's happening. Let me stop that share and share the wrong screen. Share this one.
So a few more questions.
Yeah.
One from Ivan Lopez. Are there some data sets from South America available in this environment? I think if you're talking about ground motion data sets, there are data from South America for subduction earthquakes, which is not part of our current data set, but we're going to be adding those soon. So there will be some motions from Chile, other countries in South America and Central America as well. In general, if you're looking for data about natural hazards in South America as a whole, hurricanes, wind, floods, all that kind of stuff, there is the HazMapper tool and the Recon portal that you can check out in DesignSafe, and it shows a map of where all of our data are. Then the second question is one that I think Charlie may be able to answer.
Yeah, sorry, I'm going to the DesignSafe to show people where that is, the HazMapper and the Recon portal.
Oh yeah, thanks.
So
the second question is whether artificial intelligence is a good solution to the problems that we showed here. Yeah, I think artificial intelligence is a useful tool for a lot of applications. Ground motions happens to be one where we have a lot of data. A lot of time in civil engineering or natural hazards, we don't have a lot of data, and it probably doesn't make sense to use artificial intelligence if we just don't have much data. This is one where, the ground motion database has 192,000 data points, so it's quite a few. I'm kind of a skeptic in a lot of ways of AI. I think that, when you build a neural network or a random forest algorithm, it can be a lot more accurate, but you sacrifice some explainability. And so, there's always trade-offs. If you can make a model where you can clearly explain every part of the model and it's equally accurate, I would prefer the heuristic model every time. But sometimes you just can't get there, right? And then the AI is necessary to provide the level of accuracy that you need. So it's always a trade-off between accuracy and explainability. And Charlie will show some of that, right? I don't know, Charlie.
Yeah, I'll dig into some of the ML models at the next webinar, the part 2 to this one, where we'll talk about like the different like random forest regression models, for example. We'll may even do some forecasting models to see exactly what the data looks like. But the big thing I really want to hit with that one is there's restrictions. I'll just give you a little preview. There are restrictions to some of the models you can use. The number of data sets or the number of rows you have and how big the data set is, the type of questions that it answers, and exactly how it goes about answering it. So those, stay tuned for the next time. But yes, I will say this, AI's got its place. ML's got its place. You just have to understand what that place is, and just to wrap up here real quick and some final thoughts on that. Once upon a time, computers were meant to give you 100% accurate answers, right? Now we're back to that entire thing. We're just looking for an estimate. So that is where essentially AI ML comes into play is giving good estimates. But then again, you still have to realize garbage in, garbage out. So, you put garbage information into an AI, you're going to get garbage information coming out of the AI. But we'll talk about all that at the next webinar. So we appreciate everybody's time. Thanks again, Scott. Real quick here, the DesignSafe training archive is located at this URL. Just grab it off of Go to DesignSafe, go to the Learning Center. You'll be able to find the archive there. All of our posts are up there. And finally, Scott, thanks a lot for your help. Really appreciate it. Really appreciate your time. And of course, thanks to Ellen, Tim, Dan, head of our website, and Natalie for organizing these. If you have any questions, feel free to hit us up on DesignSafe Slack or send us an email. So great. If there are no other questions, thanks so much for joining us on this afternoon, and we'll see you all next time.
Yeah, thanks, Charlie. Thanks, Natalie. And thanks to all of you for coming.